Uh-oh.
Yes. Right. Next up, we have Alyosha Efros from UC Berkeley.
Okay. I am probably most well known in this audience for being Shiri's PhD advisor, for which I'm very proud. This talk is going to be kind of a rhyme to Allison's talk earlier in the week, and it's something I've been thinking a while about, and I tried to put it all into words not that long ago. So if you are anywhere close to AI, you have probably heard of the bitter lesson, Rich Sutton's manifesto from 2019. It basically says that annoyingly simple methods scaled up work much better than specialized methods. And I've always felt that there was something not quite right about this. And so here is my issues with the bitter lessons. First, is it really bitter? And second, is it even the right lesson? So to answer the first question, I thought, okay, what are similar lessons in other fields? For example, in biology. In biology, in the 19th century, you have Linnaeus cataloging all the little animals, doing hierarchies, having a great time, thinking, okay, I have my, 10-year job until I die, because there are so many animals and it's so complicated and it's very hard to put a hierarchy onto all this thing. And then boom, comes Darwin and kind of upsets the whole thing, right? Darwin says that actually it's things are kind of much simpler, right? It's not like he didn't explain how all of the animals relate to each other, but he proposed like this meta model, which turns out to be very simple. But was it really bitter? I don't think it was bitter. I think it was great, because simplicity, goal of science is to find simple answers, and Darwin's answer was definitely a simple one, and I think that was actually not that bitter. In physics, before Newton, as Don Gieman said right here in Berkeley in 2007, we had a workshop, and he said, physics before Newton is like miscellaneous early efforts, and he meant computer vision by that. And he was right. In 2007, it was miscellaneous early efforts, right? So, and then boom, comes Newton, and all of these previous physicists are like, oh no. But were they really embittered? And were the physicists coming after Newton embittered? I don't think so. Because again, simplicity is good. Finding simple answers to what seemed like very complicated things is actually a benefit. So, second, is this even the right lesson? And so if you look at the text, he says something like, the actual contents of minds are tremendously, irredeemably complex. And I'm not sure that's the lesson. In fact, if there is some sort of a bitter or at least a humbling lesson in what's happening in the last decade, it's a humbling lesson for humans. Because it turns out that we humans are much simpler than we thought, right? So 99% of the time, we are just this nearest neighbor machines, stochastic parrots, walking cliches, pastiches from our high school reading lists, right? And only once in a blue moon, we have this flight of fancy where we can actually transcend and extrapolate from all the data that we have seen. So that, I think, is an interesting issue for the humanities. This new Copernican revolution that we have to all deal with when we realize, we're not as smart and not as creative as we thought. But that's not really the issue of AI. That's the issue for us to deal with. So if you look again at the manifesto, it really talks most about computation. The computation is mentioned 21 times. Data, on the other hand, mentioned once, and even that is in passing. And so I think this is not quite the right way to think about it. And I know that there are some people who believe in this kind of grand data compute trade-off, right? That basically any problem you can either solve with lots of data, or if you're willing to spend compute, you don't need the data. You can basically generate your own data with the compute. So there is this kind of a equivalence between the data and the compute. And it's a nice thought, but I think it's wrong for what we are interested in. And here is my reasoning. So let's say that we want to capture, our world, right? So our current world is the data. So we need to, somehow scrape all the information from our world, and that's our data. And then the compute folks would say, well, actually, there's another way, right? You can start from the beginning, get yourself a gazillion GPUs, and just simulate from the beginning of time and get to our world without using any data, right? If you look at physicists, for example, we have some physicists on our cluster, their processes never take any input, right? Their code does not take input, it's just output. Magical, right? It's like incredible, right? So basically that's the idea. You just no input, you just simulate the whole thing, and then you get to your world, right? So this sounds plausible, but there is a very important issue here. What we want to simulate is specifically our world, not just any other world. And I think that is going to be very hard, because let's say that you are a physicist. Let's say you start at the beginning of time and you start simulating, our world. Well, there is some random decisions you have to make, right? You have to decide if the asteroid hit the Earth and the dinosaurs died, right? There's a lot of coin flips that happen in that simulation. And that vector of coin flips, that is your irreducible entropy. That is kind of the signature of our world, right? Which separates our world from all the gazillion other worlds that you could get to if you made different coin flips. And my feeling is that there is a lot of entropy in here. And this entropy is kind of irreducible entropy, that these decisions really, really change the appearance, the feel, the way that our world works. And this you cannot get from first principles. This is just how the coins landed to get us to the world we are in now. And so if we are to have a world model of our world, one way or another, we have to inject this vector of coin flips into the computer. I don't think there is any way around it, okay? And indeed, we know this. We have known this for a long time. There's this wonderful paper, if you're into from 2009, on the unreasonable effectiveness of data. There is work by Antonio Taralba and myself back in those days too, showing that it is the data that's really driving progress in AI. And yes, you also need computation. But in my view, computation is secondary to data. It's just basically like you have all this data, you need to touch it, right? You need enough compute to be able to touch all the pieces of data that you collected. So you at least need to have, O of n computation for your data set of n items. But the computation without the data, in my view, is completely useless, okay? So to me, data is primary. And we still see that today, data is still winning, even if it looks a little bit magical. So here is an example of a text-to-image model, and you type in something like, a green creature made of leaves and vines bursting out of the ground, ready to attack, and then you say, please give me an image, and boom, it gives you an image. And it's like, wow, this is magic. This is just AGI, singularities, happening next Tuesday. Well, not quite next Tuesday. One thing that we did a few years back is we said, okay, how much of this synthetic image is already in the training data? So there is this question of data attribution. And so we looked at the visual data attribution, big data set, line, 5 billion images. No human has ever looked at it. And say, okay, can we find the images that are most responsible for the appearance of this synthetic image? And I'm not going to tell you the algorithm. It's basically a version of nearest neighbor with the learned distance metric. What we found is these are the 6 most influential real images to generate that synthetic image.
Influential or similar?
Influential.
How can you tell that they were influential?
You should read the paper. Sorry. Yes. We basically set up a situation where we add a new image and then we learn which image did we add. So it's a distance learning given this kind of a add one in kind of setting. Actually, we have a number of papers in this space. But the point here is, first, I had no idea these kind of paintings were in line. I thought line was like photographs, but no, there's these paintings. And now you see, okay, it's not really that surprising maybe, right? Maybe now, given those images in the training set, getting something like this, maybe a little bit of like texture synthesis from the 90s is maybe good enough. And indeed, in the 90s, we did have something like this with Bill Freeman, little texture synthesis where you basically take a lot of patches, put them together, get something new. And there is a wonderful paper from Surya last year that basically argued that image diffusion is basically a version of texture synthesis. It basically says that it's not looking at nearest neighbors for the entire images, but it's looking at nearest neighbors of patches of images and then basically stitches them together in a way that looks okay. Okay? And they had, I love the theorists. Look at this. They have their theoretical, basically, nearest neighbor baseline, and they have the real thing, and they just match. Okay. Now, this paper only deals with convolutional diffusion models. They can't explain attention, but I feel like that will also get done. But I'm very happy with this paper. If you haven't read it, I highly recommend it. It's a wonderful paper. Okay. Another paper that I was hoping Phil would talk about, but since he didn't, I'm going to do it for him. To kind of argue for data is this new paper, one of probably my favorite paper this year, Neural Thickets, where basically he argues that pre-training is all you need. Essentially, if you have a model that's untrained or it's a small model, then if you look at the weights of this model and you just randomly walk around the weights of the model that you have other models, right? And all of these other models are really junky. But if you have a large trained model that's trained on lots and lots of data, it turned out that if you walk around, if you just perturb the weights of your model, just you walk in weight space of that model, it turns out that the nearby models are also very good. In fact, you can have models that are better than the original trained model for particular tasks. So there is a model that is an expert in programming. There is a model that's an expert in math. And what Phil showed is that you can just basically random sample in the neighborhood and get models that are better than the original model. Essentially, you can do fine-tuning, you can do post-training without RL, without fine-tuning, just by random search. Which suggests to me that again, these models already know everything because they have all seen the data. And all of this post-training is essentially just kind of telling it, it's kind of like if you are you partied the night before the exam, you show up for an exam in your class, and you have forgotten, which subject it is. Is it physics or is it chemistry? Well, the first question on the exam will hopefully tell you which one it is, and then you're good to go, right? It's basically, that's what post-training seems to be doing. It's just telling you where you are. Yes?
It's hard to prove that this is the data and not the model, though.
that's giving you this.
Well, but the data, there is no data in post-training. The data has already been seen. All of the programming data, all of the math data has already been in Common Crawl, because Common Crawl has everything.
I'm saying, like,
It's fine-tuning, you get additional data.
No, you think you get additional data, but it's still, you had this data already, because they already train on everything.
but in this,
Unless you're very careful and you find something that's really, really hard. Yeah.
in this ticket, when you go around, I mean, it might be that just the model, that the actual algorithm is very good. I mean, I'm on your side, but I think that this is a weaker. You can't prove that it's the data, not the model.
I'm hoping that maybe I can convince Phil to prove it, because I think that it should be easy to prove. But
Phil, you have until tomorrow.
yes,
This is a good question for the theorist, I think. There's a proof to be had here.
yeah. No, but look, there is no new data, so it must be, you know. Anyway, I love this paper. If you haven't seen it, please look at it. So basically, to paraphrase Arthur C. Clarke, interpolation in sufficiently high-dimensional space might be indistinguishable from magic. And you know, I really like the way that Allison talks about current AI system. She says, you know, these current AIs, they are not intelligent agents, they are cultural technologies. So, you know, it's like the encyclopedia or the printing press, right? And again, Phil has this wonderful idea or notion of data plus plus, a way to think about these models, the generative models, not as something that is generating new stuff, but as something that is basically capturing the data and the controls together into one model. So it's like in the olden days, you have your hard disk and you have all of your, you know, images and your videos on the hard disk, and then anytime you need to do something with it, you need to load them up from the hard disk. And in the model, in the generative model, you have all that code and all the data together, and they're basically one. So you don't really necessarily create anything new, but you're very, very good at interpolation of the stuff you already have. And this is really, once you have lots and lots of data, that might be all that you need. So what are the ingredients that we need for true AI? So first, I hope I convinced you, somewhat at least, that it needs to be, the focus needs to be on data and not just algorithms, okay? But is scraping data enough, okay? So data is crucial, it grounds us, but just by itself, it's basically just interpolation. It's mimicry and pastiche, right? So, you know, you can, you know, we can all have GPT, whatever, answer all of our emails and write bad poetry, but, you know, is this really going to, you know, extrapolate, right? Basically, you can think that of current approaches as basically distillation. We're distilling 2,000 years of human written knowledge into this model, right? And we know that distilled models are not as good as a real thing. They don't generalize. They don't continue learning as well as real models. There's something inferior about stealing knowledge instead of generating it yourself. And, you know, will this kind of scrape data gonna give us the next Borges or the next Bach? I don't think so, at least I hope not. So when I was a young kid in the 80s, you know, I talked to folks about AI, and one of my friends told me this wonderful idea. He said, AI is not when the computer can write poetry. AI is when the computer will want to write poetry. And so I think the second key ingredient to AI is not having an objective, to have an emergent objective, to have some sort of curiosity, intrinsic motivation, empowerment kind of thing where you don't have a task. You just want to learn about the world and to discover better data, okay? And this, now we come to this distinction I want to propose between surface data and deep data, okay? So we already talked about Moravec's paradox. This is my favorite example of it. So, you know, chess has been solved 30 years ago, but this dude right here, the dude that moves the chess pieces, still no robot can do this, okay? No, it's true, right? So if you are a VC in Silicon Valley and you want to decide if a startup is going to make it or not, very simple algorithm. You just look at how much data they have, and if they have lots of data, they're going to succeed. If they don't have much of data, not going to succeed. So, text data, great. Image data, getting there. Video data, not much, but it's on the way. Robotics data, nothing. It's nothing. There is no hope of getting anywhere. So I would be very, very worried if I had shares in robotic startups. Why? Because, well, first, there is just no data, right? It's very, very hard to get robotics data. But also, the data that is there is the wrong kind of data. It's the scraping data. So either, you're basically scraping books for text, which is a very passive thing. You're just sitting there reading, or you're couch potato sitting in front of a TV watching pixels. Okay? And even Socrates was not happy with this. Socrates did not like passive knowledge. He was actually very much against books. He said that books, they're passive, they are unable to argue, they do not engage in living dialogue, and they create the illusion of wisdom. Like, look at this. This is so relevant. And as for wisdom, you provide your pupils with appearance of it, not the reality. If they think, for they will read many things without instruction and will therefore seem to know many things when they are in most part ignorant. Nothing changes since 2,000 years. So basically what we really want is we want this living dialogue between the organism and its Umwelt, its environment. Okay? And so this is where we propose this idea of deep data. So surface data is the stuff you can scrape, right? It's the words on the page. It's photons on surfaces of your environment. It is audio signal that your ear just receives. Deep data is the data that you need to work for, you need to mine, okay? So if you look at this image, for example, if I ask you, how heavy is this knife? You might have a guess, but there is really no way for you to know except to reach out, pick it up, and capture that data in situ. What is that liquid? Is this tea or is this honey? Again, no way for you to know, but to reach out and start pouring and look at the viscosity. How do you open this silly Mac? You never know, is it this way or this way? Again, no way to know except to try. Okay? And babies are really incredible deep data miners. So here is a kind of a scary or disturbing thought experiment. Look around, or look at something that you have, phone, set of keys, and try to imagine how it tastes. It's kind of scary that we can do it. Yes? And we can do it because we have mined for this taste data, all of us, when we were kids. We actually have put everything in this room into our mouth. That's how we know. Right? And this is what you need. This is what we need to do. We need to get in and mine our environment for this deep data. It's not going to come to us. We have to be active. We have to go in and do it. And this is where kind of a big inspiration comes from Alyosha and her slogan about scientists in the crib, right? So babies are scientists. They're actively performing experiments on the world and their parents, and that is how they get this deep data. They are not scraping the world. They're mining the world. Whereas what we are doing right now, we're just scraping the surface, and that's why we're not quite there yet. So surface data, cheap to scrape, parallelizable, similar information. All the samples are more or less the same. Deep data, much more expensive. It's sequential. You cannot really parallelize it. And there's a huge variance between the value of each sample. You might get some really good samples, and then between them is just completely useless samples. Okay, so you need to be like a hunter for good samples. You have to really focus on getting the data. Okay, and the cool thing is that it's the more you dig, the more valuable the data becomes. So let's say this laptop. So let's say you're a kid and you're like, trying to figure out how it opens. So you tried different sides. Finally, you managed to open it. Boom! A whole world of new data, is given to you that you haven't seen before. This is completely new data. And then if you make the mistake of stepping out of the room for like 13 milliseconds, the baby is going to go farther and dip even deeper. And this is good. This is a very good instinct to get in and get this kind of a deeper and deeper data. So you can think of this as kind of this deep data flywheel. So you have the data, and you're training a model to get some capabilities, and those capabilities give you a way to get better data, and it just gets better and better. It's this kind of a natural curriculum. You start with the simple data and you get better and better and better. Okay, so the current ways of people doing or training for robotics are insufficient. People are mostly doing teleoperation, simulation, and learning from video. Teleoperation, it lacks scale, it's passive data, and there is no negative data. I think that's kind of the most important thing, right? So for example, LLMs, you essentially only get only the positive examples, which for language I argue is okay, because language is forgiven. You just output some text tokens, and worst case you sound like James Joyce, right? You're a postmodernist, right? Now, if you're doing arithmetic, then it gets a little bit less forgiving. So that's why you need RL to make sure that you actually output 2 + 2 is equal to 4. But with physics, with the physical world, the world really pushes back. You cannot be postmodernist if you have a robot that kind of breaks tables and stuff, right? Or breaks itself, right? The world is really pushing back, and we don't really have a good story for how to implement this pushback with something like teleoperation. Now, simulation, something that Jitendra is a big fan of. You can push back. The world can push back. You can have negative data. Everything's great. The problem is lack of realism, right? Simulators right now, they don't have visual realism, they don't have tactile realism or material realism, and even physical realism. Current simulators are not very good at physics for like manipulation. And here it's basically, if we want to have good simulators, we again need to inject all that entropy I talked about into the simulator. So we are back at the deep data problem, because somehow we need to get this deep data into the simulator. So solving this problem, we need to solve the same problem again. And we've seen this movie before. So in 25 years ago in computer graphics, they thought, okay, they solved rendering. They thought, okay, we can render all the everything, because we know all the physics, all the ray tracing, all the global illumination. But it didn't work because they didn't have the data. They didn't have a way to inject entropy from the world into their models. And that is why image-based rendering and all these data-driven methods have basically taken over graphics, because that was a way to inject data into the system. And learning from video, again, tons of data, but it's surface data, missing embodiment. Imitation is not it. Humans are good at imitations, but we're not that good. For example, I tried learning how to dance salsa from watching TV. It's not possible. You really need to get in there and do it, and I have tried, okay? So basically, what we want to do is we want to mine this deep data using Allison's scientist in the crib, using some sort of curiosity, intrinsic motivation. How much am I out of my time? 1 minute? Okay. Forget this. Basically, we want to have a robot scientist in the crib. Okay. That is the goal. And the conjecture is that if we have this goalless exploration, we should be able to collect this deep data and get more intelligent behavior that will allow us to collect even more deep data, et cetera, et cetera. Okay? And we have done something like this back a while ago in 2017, and I feel that we should get back to that. So we did this work with Deepak Pathak, where we say, okay, can we learn to play Mario Brothers without any rewards, with just curiosity? Okay, intrinsically motivated. So basically, you have your joystick, you have your pixels. Can I learn to play, right? And basically, the idea is you just try to make a prediction, and then you try it out, and then you see if the prediction is correct or not correct. And when the prediction is not correct, that's great, because that basically increases your curiosity. So we define curiosity as a prediction error, okay? And then we basically have this flywheel where we just get more and more curious about things that we cannot predict. And it gets you this lifelong learning. And basically, essentially what we had was a world model before Jan called it world model, because what we had is we had a prediction and feature space, and then we had a feature space that would only care about what the robot was interested in. So we had this inverse model to learn a feature space at the same time. So we had an inverse model to learn the feature space, and then in that feature space we would do the prediction. So kind of like a pre-JEPA, if you wish. And it actually worked pretty well in simulation. So here is an example. If before training nothing happens, and then after training, you have a Mario that is learning continuously online, passing new levels, and it's not scoring many points because it doesn't care about points, but it's staying alive, it's killing enemies, and it's going forward because that's the curious thing to do. That's the interesting thing to do. And then we also did it on a whole bunch of different other video games. This is an interesting one. This is like playing ping pong just like I do. Like, the goal is not to score points. The goal is to just keep the rally going, because that's more interesting. Okay? And then we did this also recently for diffusion models, and basically adding curiosity to the diffusion model. Sorry, I don't have time for this. And also we try to do it on text data using curiosity to explore on the internet. But still, has never worked on a real robot. Just too hard to work on the real robot. But I think that this is the right direction. So in summary, surface data is enough for some magical things, but I fear that we are not going to go beyond this mimicry and pastiche. And to go farther, we need this deep data. I believe that curiosity or empowerment is the right way to go, but we are just at the very beginning of it. And the slogan is, ask not what the data can do for your robot, ask what your robot can do for data. I imagine this beautiful future where we have little completely useless robots just scrolling around, gathering data for next generation of better robots. We have a paper with Ilya Radosavich that we wrote last year, but we still haven't been able to publish it. But if you want to preprint, let us know. And just recently, Rich Sutton published a new paper that is actually very much agrees with us, and he mentioned data 18 times. So we feel like, things are getting better. So thank you very much. Sorry for running over. Yes.
So I would like to ask if, to some extent, the surface data can be converted maybe not to the full deep data, but partially there. For example, in your example here, you ask whether it's water or tea or honey. Well, probably tea, because, who puts a cup of honey next to the computer? And the computer probably opens on this side and on that side, because the forks are here. So yes, I don't know exactly how much the fork weighs, but probably less than the computer and maybe less than the cup. So somewhere I can get there, not fully.
Yeah. I think this is exactly what Socrates called the illusion of knowledge. You can get a lot a long, long way through just these kind of correlations. It's probably C and not honey. And this, I believe, is what current AI is all about. It is just using these correlations and just hoping for the best and being correct most of the time because, because this it works. But that's, I think, where we are lacking the deep understanding. You think it's probably honey, but you really don't know, and you don't know how to test. And so I argue that it's true that surface data get you very far, but I don't think it can get you to extrapolate. I think it's all about interpolation. But I might be wrong.
So Daniel, in his conscious Turing machine talk, said that there is a difference between the suffering of pain and the knowledge of pain. So likewise, there could be a difference between the pleasure of satisfying your curiosity and the knowledge of satisfying your curiosity. And so I'm not trying to diminish your proposal of deep data. I'm trying to thinking about the possibility of something above that, like maybe deep plus data.
I don't know. I'm not sure. Okay, there is the issue of the deep data, and then there is the issue of how you get there. And my feeling is something like curiosity, intrinsic motivation, empowerment is a way to trick the organism into getting that data. But maybe we're wrong. Maybe there is some other way to getting there. I don't know. I think this is our best guess, right, Alison? That's what we think is our current best guess, but maybe there is something else. But I think this is separate from the actual existence of deep data. Yeah?
I was quite stricken by the contrast between the severity of some of your statements and the paucity of the data that you provide.
Okay, but this is supposed to be a workshop with lots of hand waving.
For example, you say current AI cannot be creative and just, interpolating, and all you had to show for this is just one image that you found there as other images. Wouldn't you think that to say this, what you're trying to promote, would require much more than finding just some similar thing? How would you go about to really prove to me that AI is not creative and just interpolating?
I don't think I even care about proving this. This is all about, we're all. These models change every 5 minutes, right? It's all about speculating about the future. My feeling is there is going to be a limit to the creativity of these AI models. Now, if you want some proof, the Surya paper is a wonderful theoretical paper that actually does prove something. It actually has the word creativity in the title, right? But to me, it's really just kind of guessing about what's coming next. I could be wrong. It might be that the current setup is enough. I don't believe it. And I think maybe Alison has a wonderful paper in Science, right? You have this paper on the cultural technologies. Do you have any proofs? I don't think there is any proof. I don't think you can have any proofs. But it's, I think this is the, there is a scientific method which we're taught in school, and then there comes what comes before the scientific method. Because there's infinitely many hypotheses. Which one do you test? This part is basically art. Good scientists pick the right hypothesis to test, and we're all trying to be good scientists, but it is that part of science is art. That afterwards comes the actual testing and the science. Jitendra.
So there's a Gibsonian notion of active perception, right? That the data is not collected passively, but the agent, animal,
That's
whatever, chooses what data to collect, and it's always a loop.
That's right.
So we see in order to move, and we move in order to see.
And Van Uxel's story is also.
Yeah. So basically, is your deep data just data acquired with active perception?
Yes, but it's it's not just that the data is acquired actively. It is that the activity is focused on finding good data. So basically the idea is that the robot is not actually doing any task. The task of the robot is to acquire better data. So it's not like you're willy-nilly, oh yeah, I'm going to acquire this and this. No, you're focused on, like, this is your life's goal, is to find deep data.
But Gibson's notion is that, right? Because, for example, I mean, what he said was that we don't just passively acquire images, we choose what to acquire.
That's right.
And then what we have acquired determines what we acquire next.
Yes.
For example, so he gives the example for tactile, but he says that actually
Right.
is like that.
No,
Choosing the next touch problem.
That's right.
The next,
That's right.
Next gaze problem.
That's right. No, we are definitely very much Gibsonian and Van Uxwellian in that sense. Yes. And I think this is a kind of a contrast to scraping, common crawl as the kind of the what we are fighting against. Yeah. Alison.
So I think this connects to Jitendra's question, and a question I've been thinking about, which is how does this relate to RL, right? Because in a sense, RL is doing deep data, right?
Yes,
It's actually
absolutely.
going out and
Yes.
it's doing actions and
Yes.
it's intervening.
Yes.
But the intuition, which I think has some technical force as well, is that just doing that in the service of the goal, which is one of the things that a kind of Gibsonian picture would be. You want to get to this, so then you have to find the right data that will let you get to this, is different from the kind of epistemic curiosity exploration. This is a explore, exploit, essentially.
That's right.
And my intuition, and I think your intuition, is you can't just solve this problem by just revving up the goal-directed kind of classic RL.
That's right. That's right.
But I wonder and the way that RL gets used in post-training, for example, is pretty boring, right? It's just, does the person like this, or does the person not?
That's right.
And in terms of the question about data, maybe this is just the ill effects of philosophical training, but I do think there's a sense in which you could say, all right, given the way that these systems are trained, there's only just so much that they can do. That's just the nature of what these systems can do. And then there's going to be other things that, just given the structure of how the systems work, are not going to be the things that they're going to do. Or what they might be able to do is simulate them with a bunch of extra instruction and tuning, but the systems themselves, those algorithms, are not going to be able to do it, no matter how much data they have.
Yeah, no, I completely. I think RL we're exactly halfway there with RL, because it is mining for deep data, and in fact, this is where the successes of RL are for things like Go and coding.
Yeah.
It's a small enough environment, and it's a constrained enough environment where the goals are very clear and clean that we could mine for deep data in those constrained environments. In the real world, though, this is much harder, and exactly, I completely agree with you. It's basically because RL usually is used with an objective, with a fixed objective. And to me, the inspiration from evolution for me is that it's something where the objective is not fixed. The objective itself evolves. And I feel like, I was really excited when we were in the world of GANs, because GANs had this flavor of an evolving objective. And I wish we could kind of somehow get back to that a little bit. And so, in a sense, like our old curiosity work is kind of like that, but it's not quite there yet. But I agree. It's this intrinsic, something intrinsic that is driving us, that should change over time, that should not be fixed.
Correct.
Yeah.
Alyosha.
Yes, one more. Oh, pick one.
Well, you choose.
No, I cannot see anything. Okay.
I just want to press you on your commitment to embodiment and what you think the implications might be for other people in the room. I'll just leave that question short.
So I feel like this kind of deep data should also help other areas, not just robotics. It is very annoying how much data we need for let's say computer vision tasks, right? So the classic Teralba calculation is you need about 80 million images for a baby to learn to see, and we are many orders of magnitude off from there. And it might be that if we were somehow using this deep data instead of just scraping all of the data, we might lower the amount of data that we need for not embodied tasks as well. I think for embodied tasks are where the biggest problem is, because right now nothing works in robotics. So this is the most pressing issue. But I think this should also help in other domains as well. Yes.
Thank you very much. Okay, before you leave, I have an announcement. We are missing a backpack from yesterday that was left inside the auditorium, or so we think.